I'm going to illustrate one of the applications of a 3 by 3 determinant. We're going to write the equation of a line passing through two given points. And the points are going to be -3, 4, and 2, -2. Now I could do this in algebra by finding the slope and then using the point-sloped formula. But an application of determinants is I can set up a 3 by 3 determinant and set it equal to 0. To set this up, we put the variables x, y, and then a 1 in the top row. We put the first ordered pair, followed by a 1 in the third column, the second ordered pair, followed by a 1. Now I'm going to expand this determinant using minors. So I would take x, the element x, and write it down. Multiply it by the power of -1 from where it came. Since it's in row 1, column 1, 1 plus 1 gives me a square for that -1. And then I would multiply it by the minor I get by marking out the row that contains x and the column that contains x. So I would mark out the top row in the first column, and I'm left 4, 1, -2, and 1. So I'm going to write those numbers down. 4, 1, -2, and 1. 4, 1, -2, and 1. And then I would take my second element in the top row, which is a y, plus y, and the power of -1 I need. Since the y is in row 1, column 2, I add 1 plus 2, the subscripts, to get the power of 3. I'll multiply that by the minor associated with y, which I find by marking out the row that contains the y and the column that contains the y, and I have these four numbers left, -3, 1, 2, and 1. So I'll write those down. -3, 1, 2, and 1. And lastly, I will take the third element in the top row, which is a +1. I'll multiply it by the power of -1, which is fourth power, because it sets in row 1, column 3, and 1 plus 3 is 4, times the minor that I get by marking out the row that contains the 1 and the column that contains the 1, and these four numbers make up the minor associated with it. I'll write those down. -3, 4, 2, and -2. -3, 4, 2, and -2. Now what I'm going to end up, I'm going to have a product of three numbers right here to add to a second product, to a third product, to get a final answer. Remember, this is all equal to 0. So I have x times -1 squared, which is +1, times, I say 4 times 1 is 4, minus -2 times 1. 4 minus -2, that is the determinant for that little minor, plus y times a -1. -1 cubed is -1, and then over here I do -3 times 1. -3 minus 2 times 1 is 2, that's a -5, plus 1 times, this is a +1, times the determinant right here, which I get is -3 times -2, 6, minus 2 times 4 is 8, times -2 equals 0. So I'll have 4 plus 2, I'll have 6x. Y times -1 times -5 is +5y, minus 2 equals 0. So that is the standard form. In standard form is ax plus by plus c equals 0 of a line passing through 2 points. Now to check that by the old traditional way, I would find the slope of the line containing these points by negative 2 minus 4 divided by 2 minus negative 3. I'm getting negative 6 divided by 5. And then I would use the point slope formula with that slope. In one of the ordered pairs, I'll just use the second ordered pair for x1 and y1. And the point slope formula is y minus y1 equals m times x minus x of 1. So I would have y minus negative 2 equals m times x minus x of 1, 2. Solve that out. Y plus 2 equals negative 6/5 x plus 12/5. Now I could clear my fractions even right here by multiplying the entire equation by 5, the denominator 5, to get 5y plus 10, 5 times 2, equals negative 6x plus 12. Because over here on the right, the denominators cancel out, and I just get that. And then I want this 6x term moved over to the left, so I will add it, and I have 6x plus 5y, and I subtract 12 from both sides. There's where I get the negative 2 equals 0. So you see it gives the exact same answer as we got by expanding this 3 by 3 determinant set up in the right form. And that's just one of the many applications of determinants.